Okay, so today we're going to move into the next phase of the course where we start building a CPU. We're going to build a MIPS CPU because you should all know MIPS pretty well from 212. That's the reason why we were thinking about switching the course to RISC-V, which is a more of a contemporary instruction set. But then we'd have to teach RISC-V, and so we're hoping that everyone remembers MIPS. But just in case you don't, or if you've forgotten some of it, I'm going to briefly review that. So MIPS is the architecture, and we are building the microarchitecture. The architecture is the interface between the software and the hardware. It's the assembly language, the machine language. And the microarchitecture is the underlying implementation. That's the circuits that execute the programs. So one of the nice things about MIPS is that it's very simple. It only has 3 instruction formats. And the J type is only used in a few instructions. So mostly it's just all the instructions are R type or I type. And I think this is the reason why MIPS has been around so long and has been as popular as it's been. RISC-V has, I think, 8 instruction formats. It's much more complex. So having just the 3 simplifies things tremendously. I know Intel has quite a few. IBM's got a bunch. ARM has a bunch. ARM doesn't have as many as RISC-V, I don't think, but MIPS has the crown when it comes to a simplified instructions. The R-type instructions are, I think R-type stands for register type, although I'm not sure about that. That's what I've always assumed. R-type instructions are instructions that are 3 address instructions. They take 2 inputs that are register addresses, or register numbers, and there's an output register number. So generally speaking, they take data out of the register file as addressed by the RT and the RD. Now there's some exceptions to this, but normally they read 2 registers, they do something, and then they write the result back to the RD field. And sorry, I was pointing at the wrong ones. So one of the confusing things is that RS and RT are usually the inputs, the input operands. RD is the destination, but in the assembly language, the destination comes first. You guys remember this, right? So you have like add, register 2, register 3, register 4. So you're taking register 3 and 4 as the inputs, and register 2 is your destination, your output register. So that's your RD. Register 3 is RS, which stands for register source. And RT, don't know what the T stands for. I always think of it as a toggle, because it could RT for an I-type instruction. Sometimes they'll use RT as the destination.
So target and source. Target,
maybe, yeah. I'm not sure, but yeah, RS and RT for this instruction are your inputs, and RD is your output. This depends on the assembler, though, and so if you write assembly code in other instruction set architectures, sometimes the destination will be last. Like GNU GCC, or the GNU assembler, famously has this reverse where they put the destination on the end. I don't know why. If you look up the documentations, they say GNU uses AT&T syntax, which always puts the destination register last. I don't know what that means, but that's what they say in the docs. MIPS typically, at least in academic courses, they use this format where they put, but that's not always the case. But the crazy thing is that if you look at the instruction format, notice that RD does come last in the instruction encoding format. So, in other words, when you take the assembly and you convert it to machine code, you have to move the RD to the last position, to the rightmost position. And there's also a shift amount in there as well, which is a don't care unless you're doing a shift instruction, such as shift left logical, register 2, register 3, and then the shift amount. So in this case, register 2 is your destination, 12 is your shamped, your shift amount field, which can be 0 to 31. And register 3 is, well, you would assume it's RS. But it's not. It's actually RT. Unclear as to why they do that. So for shift instructions, the RS field isn't used. They use the RT as the input along with the shift amount, and the RS field is a don't care. You just have to kind of memorize that. There's no rhyme or reason to that. If you notice, though, in your ALU design, whenever you do a shift operation, you're shifting the B input. I don't know if you guys noticed that in the code we gave you. And the reason for that is because the ALU associates the A input with RS and the B input with RT. So by having the ALU hardwired to shift the B input is the way that once you drop that ALU into your CPU, it'll shift the RT register, which is what MIPS dictates. Okay, any questions about that? Okay, so converting assembly code to machine code is based on taking a 32-bit instruction, all the instructions are 32-bit in MIPS, and dividing it into these fields. The only field that is common to all three instruction formats is the opcode field, which is the most significant 6 bits. So the idea is that use the first 6 bits, the leftmost 6 bits of the instruction, which is bit 31 down to 26. You use that to determine what the instruction is and what format, or well, what format's in. I shouldn't say what it is, because with R-type instructions, you always have, all the R-type instructions have a 0 opcode. You guys remember that? Okay, so, and this is pretty common in other architectures to have a bunch of instruction formats, and then you have just the opcode is the only common field. So they use the opcode to figure out what the other fields are in the instruction. So in the R-type, it's 6-bit opcode, which is always 0, and then 5-bit RS, 5-bit RT, 5-bit RD, because the 5 bits, why? Because there's 32 registers. And then the shift amount is also 5 bits because the registers are 32 bits wide, and you don't want to shift any more than 32 bits. So that's just 5 bits gives you a value between 0 and 31, and it's unsigned. That's an unsigned shift amount. And then the function code is the last 6 bits, the least significant 6 bits, and that's what you use to determine which of the R-type instructions you're executing. Now you might say, why do we care about any of this stuff? In 2.12, you probably didn't focus on this too much. You didn't. I'm sure you covered it, but there wasn't a lot of emphasis on how you take an assembly instruction and convert it to a machine instruction. Understandably, it was kind of just a kind of a footnote in that class. But in this class, it's important because you're designing. Your hardware is going to be seeing the machine instruction, right? You're writing You're writing a Verilog code that is acting on the machine instructions, right? So it's really important in this class that you understand how the assembly maps into the machine instruction, right? So anyone have any questions about that? You guys remember that? Okay. Okay. And the I-type is taking the RD field out as compared to the R-type. The I-type removes the RD field and the shift amount field and the function field. So that's, the RD is 5 bits, the shift amount is 5 bits, that gives you 10, and then the function is 6 bits, that gives you 16. So you trade off those 3 fields for a 16-bit immediate value, which is a constant value that's put right into the instruction. It's compiled into or I should say assembled into the instruction. So this is used for whenever you need a fixed sort of offset, right? So load and store instructions actually have an address offset that you can put in there. Branch instructions have an offset that determines how far they branch, and that's a constant. Why? Because the branch behavior in terms of how far it branches when the branch is taken is something that's locked in when you assemble the code. And it's also used for like loop counters and that kind of things and initializing variables. You guys with me? All right. Okay, so the RS and RT are in the same positions in the I type as they are in the R type, except the RT, as I mentioned earlier, the RT is sometimes a source register and other times it's a destination register depending on which I type instruction you're executing. Okay? Okay, and there's some examples of I type instructions. And then finally there's the J type. The J type is, we're only going to have two instructions in this class that use the J type, the jump and link. And the J type is opcode and a 26-bit address. In this class, we will have less than 26 bits of instruction memory. So as a result, we can put the whole target address in here in this field, right? So if you have a jump instruction in this class, you can take the whole address you want to jump to and you just stick it in this field. You don't have to worry about, how you reconcile the 26-bit limitation here with, your actual address space, which might be more than that. In this class, we'll have a smaller address space. You guys with me? So in other words, this is a direct address. You just take the address you want and it goes inside that field. And jumps are so these are only used for jump instructions, which are unconditional change of control. Yes?
What would we do if the address was greater than our address space?
Oh, if it's greater than, you just ignore so that'll actually be the case. We're only going to use, Charles, what did you say, 4096? 12-bit. So we're going to have a 12-bit instruction address, and the instruction addresses this is an instruction address, so it's a word address. So if you think of it as a byte address, we'll have a 14-bit address. But jumps are this is the word address. This is a word address in here. So in terms of word address, when I say word addresses, I'm talking about 32-bit chunks, right? In terms of word addresses, we're only going to use a 12-bit address. So you just disregard the other bits. Right, which is typical. I mean, like I said, if in any R type that's not a shift, you disregard the shift amount field, and if it is a shift, you disregard the RS field. So it's pretty common. Oh yeah. Well, if you could hide data in there, that would be ignored by the processor. In the upper, whatever 26 minus 12, right, 14 bits.
Fun fact: Microsoft
Yeah.
did this back in the 80s. There was a reserved section of the address on I-286,
Yeah.
which Microsoft Xenix used for status flags, which is why Xenix will, at least that version, would not run on the I-386 because they ignored the warning that said, "Warning: this is not usable now, but it is reserved. Don't use it."
Don't use it. Xenix was Microsoft's version of Unix.
Oh, wow.
Right. Right.
Oh, wow.
Which is what ran the point of sale machines when I worked at Radio Shack in 1995. Okay, so yeah, R type, I type, J type. Make sure you understand that well. If you have any questions, look back at that material or ask us. Okay, so let's skip over this stuff. Yeah, so in this class, we are going to build a CPU that will execute all the instructions on this list. And I forget how many there are, 30 or so instructions. I mentioned in class, I think I mentioned last time that these instructions are, I think, the most commonly generated instructions from compilers. So this means that with these instructions, not only is your CPU Turing complete, meaning that it could solve any problem that can be solvable by any computer, but you can also compile code for it with GCC, And it's very unlikely that GCC will emit an instruction that's not on this list, even though MIPS has a lot more instructions, but they're just more obscure ones, right? Now, how many instructions could MIPS possibly have? Well, I mean, if you take, the I-type and J-type instructions rely just on the opcode field, right, which is only 6 bits, so that's only 64 instructions, and then the R-type instructions add an additional 63, right? So there can't really be much more than 100. Now, there are some hidden, we'll find out later this semester that some of the branches have function bits inside the instruction in the RT field. So there's a little bit of, there's some tricks you can play, but in general, MIPS can't, I don't know how many instructions MIPS has, but it can't have any more than, much more than 128. So we've got about maybe a fourth of the whole instruction set here. It's not too bad. And of course, we will also have access to any pseudo instructions that decompose down to these. You guys with me? Right? You guys remember pseudo instructions? They're instructions that when you assemble them, they get converted to one or more other instructions, almost like a little sub-program, like a little macro. So these are all the ones that we want to do by the end of the class, that we want to have implemented by the end of the class. The ones in red are the instructions that we are going to assign to you today. Now you might say, wait a second, there's a lot more red ones than black ones. Yeah, the red ones, though, are the easier ones. The branches and the jumps and the load and store word are going to be more challenging. Most of the red ones a lot of the red ones are very similar to one another. Like, for example, add and subtract are the same instruction. The only difference is what the ALU does, right? But everything that happens inside the CPU is the same when you execute either one of those. The add U instruction is kind of something that's unique about MIPS. MIPS is the only instruction set that I'm aware of that cares if you have an overflow when you do an arithmetic operation. An integer, I should clarify that, integer arithmetic. I think other processors will throw an exception if you get a floating point overflow. Or maybe not, I don't even know if that's true. But usually computers don't care if you overflow the integer. You guys with me? Like, so if you write a C program and you do an operation and you end up with some value in a register that exceeds the type, right? You overflow. You try to store 5 billion into an integer, for instance. MIPS, though, had this thing where it would throw an exception if you have an overflow. Now, what does that mean? What it means is if you have Linux running on a MIPS processor and there's an overflow, it'll crash the program. You'll get a seg fault and you're done, right? Whereas you run the same thing on an Intel, it'll just ignore it. So MIPS has this add U and sub U variance, which U stands for unsigned, but it's kind of misleading because it actually just means don't trap on overflow. And so a lot of compilers and a lot of pseudo instructions will actually use the add U and sub U variance just because they don't want to deal with their, any overflow. So in this class, we're going to be treating the add and the add U the same, but we have to implement them both because otherwise things would break if we have a pseudo instruction that generates the unsigned variant. You guys with me? So there's no difference between the add and add U, and there's no difference between the sub and sub U in our class. And we don't implement exceptions, so we don't have to support the overflow exception. Yes?
What do we do in divide by 0?
We don't have a divide instruction, so.
Oh yeah, that works.
Yeah, I tried. I tried to put a divide instruction in, but it ate up the whole FPGA. But that was the old FPGAs. I haven't tried it on the new FPGAs, the 115s. But I think most processors don't have divide. The ARM processor doesn't have divide. The processor that's in your cell phone can't do a hardware divide. Most embedded processors won't do divide. That's virtually unheard of. Divide is something that, in general, it's one of those. It's a cost-benefit thing. Divide is very expensive to implement in hardware, and it's almost never needed. So, if you ever have to do divide, generally, the compiler, if you don't have hardware support for divide, the compiler just converts it into an emulated divide, a software version of divide that just uses shifts and subtracts. So in my other class, 313, we use an off-the-shelf processor that we put on the FPGA, and in that case, you have an option for enabling hardware divide, but by default, it's turned off. And I think we just leave it off. So. And we won't have divide. In the lab we're assigning today, though, we actually need to do a divide, and we have a way that we're gonna work around that, and I'll get to that soon. So we've got, let's see, we do have multiply and multiply unsigned, and you guys probably knew that was coming because we have that we had that in the ALU. Set less than unsigned, set less than immediate. Those are all just ALU operations that we've got. We've got the logical, bitwise logical and/or, nor, XOR, as well as the shift, the 3 shifts. And then we have move from high, move from low. You probably have an idea of what that's all about. Remember the ALU had a high and low output, and the high was only ever set or ever used for the multiply, right? And multiply unsigned. The MIPS architecture has a thing where if you do a multiply, it stores the 64-bit result of the multiply in the high and low registers, and those registers are not part of the standard 32 general purpose registers. So whenever you do a multiply, you have to follow that up with another instruction or 2 instructions that move, and it's not really a move, this is a misnomer, it's really copy. You're copying, these instructions copy the contents from the high and the low registers to one of the 32 general purpose registers, right? Or I should say 31 general purpose registers, because you can't use 0. You guys with me? Make sense? Okay. And we're going to need those for the little programs we're going to write in the class. And then there's a no-op instruction that does nothing, but as it turns out, the no-op is actually a shift left logical, because shift left logical is an R-type instruction, which means that it has a 0 opcode, like all R-types, but also has a 0 function code. So any the no-op is just an instruction of all zeros, 32 zeros. So that instruction actually maps to a shift left logical with a shift amount of 0, and it puts the result into register 0. So it has no effect. But the control unit in your CPU will see a no-op as a shift left logical. You guys with me? Likewise, the assembler will assemble the no-op as a shift left logical. Okay. Okay, I mentioned that MIPS has 32 registers, which is pretty common. When I was in grad school, I thought, well, you know, in the future, CPUs will have more than 32 registers. And it never happened. The most advanced CPUs in the world just have 32 registers. And there's a reason for that, because the register file is supposed to be small, because it's designed to, it has to be the fastest memory in the computer, is the register file. Also, level 1 caches are so fast that it only costs you a few more cycles to spill registers out to memory if they're going in the level 1 cache. So the Intel processor only has 4 registers, and it always has A, B, C, and D, because they're still using their old 1970s or 70s era instruction set. So you might say, well, how can any CPU get away with only 4 registers? Well, they just, they just spill to, they use loads and stores. They don't keep things in registers very long. Some of the registers have special purposes. Hopefully you covered this in 212. Register 0 is always 0 when you read it, and if you write it, it has no effect. Register 1 is reserved for the assembler. This gets students in trouble all the time in this class and in 212, because if you use register 1, you may have a bug introduced in your code from the assembler, because the assembler might use register 1 when it expands a pseudo instruction, and you may not be aware of that. So you should stay away from register 1, because the assembler might clobber it. Registers 2 and 3, by convention, are supposed to be used for function return values, which is kind of odd, right? Because functions only return one value, at least in any language. Well, except for MATLAB, I guess.
Or Python.
Python, you can return more than one value in Python?
Well, you return tuples and it looks like return.
Oh, okay. Yeah, but I mean, you could argue that in C you could return a struct or something, which could have as many things in it as you want. But you can return two, sort of register values from a function using V0, V1. Function arguments are by convention 4 to 7. Of course, you're limited to only 4 arguments there. Any more arguments are conveyed on the stack. Temporary values are T0 through T7. Why are they temporary? Because if you call a function, when that function returns, it may have destroyed T0 through T7, and it has the functions don't have a responsibility for saving those on behalf of the caller. So, but we're not going to be doing anything that sophisticated software-wise in this class. Local variables S0 through S7 are for local variables, are supposed to be saved across function calls. A couple more temporary values, actually T9, T8, and T9, so there's 10 temporaries. K0 and K1 are supposed to be reserved for the OS kernel. Never run into that before. And then there's the global pointer that points to your global space where your global variables live. Stack pointer points to where you would put the next thing on the stack, and the frame pointer points to the thing that's at the top of the stack, much like the RPN calculator you guys did, where you had a stack pointer that points to the next allocable part of the stack, and then you had another thing that pointed to the top element of the stack. So that's what the stack and frame pointer are for. And then the return address for function register 31 is where the jump and link instruction and the jump and link register instruction will put the return address, so you can get back to where you came from when you call a function. And we will be implementing those instructions. The program, I'm sorry, I take that back. Jump and link register allows the programmer to specify a different return address register, but I've never needed to do that. 31 is typically what you use. And then the program counter is like high and low. It's a special register. The program counter is not an addressable register like these guys are, and the program counter points to the address of the next instruction to be executed. So it keeps track of where you are in the program, where the CPU is in the program. Obviously, if you have a multi-core or a multi-threaded processor, you need to have one program counter per thread, right, as well as one register file per thread. I just also want to point out that these are general purpose registers, as opposed to like a register that you create in your Verilog code. That's a different type of register. That's not addressable. You guys with me? So these are addressable registers. This is kind of the software concept of a register, whereas in Verilog, if you say always underscore FF at pos edge clock, A reg equals A, that's a register as well, but that's a hardware register. Okay? The terminology can be confusing. Okay, so we're going to write a little bit of MIPS code in this class. Why? It's not a programming class. Well, we need to test our processor. You need to write small programs to test your CPU, right? Otherwise, you won't know if it's working. So we use Mars. I think you guys are familiar with Mars from 2.12. Mars is great. I like it. It's getting long in the tooth. But it's nice because you download a jar file and you can just run it on any platform, and it works well because it also has the editor and the debugger and the simulator all in one package. Back in the old days, before Mars, we used to use a program called SPIM, which is MIPS spelled backwards. But SPIM was just a simulator, so you had to use your own editor, and it was a lot more limited. Plus, it only ran in Windows and Linux. So people with Macs are out of luck. Okay, so here's a quick example of how you would convert a for loop to MIPS. How would you do that? Well, the trick here is understanding exactly what a for loop is doing. For loops have this first part that sets up, that does the initialization, that runs once. Notice how I had to choose a register here for I, right? I had to allocate a register. Registers are allocated, just like memory. You know, you have a variable in a program, and then you have to associate that variable with some register. Which register? I don't know. You got to pick one randomly somehow. Why did I use S0 for I don't know. I just picked it randomly. But once you pick it, you have to remember which one, you know, what the registers are being used for at each line of code. Because keep in mind, too, you only have 32 registers, so you have to recycle registers. Once I get done with this loop, I can use S0 for something else, right? So the registers, the purpose of each register is dependent on where at in your program you are, right? So I'll take 0, I'll put in S0, that'll be my I, and then n is another variable. In this case, n is an input variable because it's determining how many trips through the loop I take. So I'm going to have to load that out of memory, and I'm going to associate that with S1. Now, the problem is that I have this array indexing where I use I as an array index. But here's the problem. MIPS doesn't have any concept of an index, an array index. MIPS doesn't help you with that. You can't specify an index register in MIPS. So you have to take these indexes and you have to calculate your own addresses, your own effective addresses. Well, in this case, it depends on the type of A and B. And in this case, I'm assuming they're integers. So every time I want to access A or B, I have to take I and I have to multiply it by 4, which is the size of an integer, and then I have to add that as an offset to the base address of A and B, right?
So A and B are static variables here? Because they have a fixed address in them?
Yeah, I'm trying to remember. Yeah, so B. Yeah, so in this case, I'm saying B, so I'm using B and A as symbols in here. Now, in this case, these would be converted to pseudo instructions, right? Because how do you specify a symbol in machine code? You can't. You can do it in assembly, but not in machine code. So these load words here and store word would be converted into a sequence of 3 instructions that would use register 1 to initialize register 1 to whatever address A and B are at, and then it would use register 1 as the base address, the base register, sorry, for the load and store. You guys with me? Okay, and then in this case, I'm adding 4 instead of 1 to I because I'm using that because I'm walking by 4 bytes at a time through A and B. And likewise, n, I had to multiply n by 4, so I can compare that to n. Right. Okay, any questions, you all? Is that coming back to you? Okay. Okay, so we want to build a CPU. We're going to use on-chip memory for our program. So that way we don't have to deal with talking to an external memory like a DRAM. That's non-trivial because you have to have a DRAM controller, and then you have to synchronize with it. So we're going to use on-chip memory. You guys, any of you ever programmed an Arduino before? They have on-chip memories too. They don't have an external. Most computers have an external memory, right, that the program gets loaded into. But very lightweight embedded systems will have an on-chip memory, and that's what we're going to use. We'll also use an on-chip memory for the data, and so how do we begin this? Well, hopefully you remember the 5 steps of instruction execution from 212. There's fetch, where you fetch the instruction, then you decode it, And I used to always be confused by decode. I was like, why do they call it decode? Because decode is where you read the registers. You read the source registers out of the register file, right? So how is that decoding? It doesn't make any sense. Well, they call it decode because you are reading the registers, the input registers, in the decode phase, but you're also taking the instruction, the opcode and the function code of the instruction, and you're decoding them into control signals. Some people call them microcode, like control word. That's a decode. Decode is anytime you take a binary value and you convert it into a wider binary value. And that's kind of describes what's happening when you decode an instruction from its encoded format, which is the MIPS encoded format, to an array of signals that kind of set up the data paths in the CPU to execute that instruction. And then there's execute, is when the ALU is invoked and does its thing, it's number crunching. Memory is then when you access off-chip memory for a load or store. It doesn't have to be off-chip. As I mentioned, we're using on-chip memory, but you access the data memory, rather. And then the write back is when you update the register file with the result of your calculation, if necessary. So here's a kind of a picture of what it'll look like. We're not going to implement. If you go back to that slide where I had the instructions, we're not going to implement load word and store word in the first lab. We're going to leave those off for now. So we're not going to do loads, stores, and control instructions, branch and jumps. So we're not going to put the data memory in, so I grayed that out. We'll have an instruction memory. That actually needs to be updated. So that says 10 bits. We're changing that this semester to 12 bits, so it's not a big difference. But we wouldn't have enough room to have 4K instructions, which is 16 kilobytes worth of instructions. So that'll go out to this instruction memory, and then the instruction memory will send back a corresponding instruction at that address. And so the CPU will be everything that we need to take that instruction and execute it. Outside the FPGA, we'll bring in a clock signal, and that also needs to be updated. Sorry, that should be clock 50. When I first made this, I was scared that our CPU designs wouldn't run at 50 megahertz. I thought that they might, they wouldn't satisfy the setup and hold constraints, right? Because if you don't, depending on how well you design the CPU, it may not run at 50 megahertz. So I used the 27, but it turned out that 50 is okay. So we should be okay with the 50 megahertz. The reset is coming from key 0, so we can have a way to reset, reset button, just the rightmost key. And then in terms of the input and output, like how does the CPU communicate with the outside world? We're going to use the switches from the board. The little toggle switches is the input, and the hex displays is the output. And so in order for the hex displays to work, we're going to put the 7-segment decoders inside that hardware as well. That way, the CPU just outputs a 32-bit value, and it will be converted to the hexadecimal digits that you see on the board. And we already have the decoders. We'll just reuse our decoders for that. Okay, so we have the 5 stages: fetch, decode, execute, memory, and write back. But not all instructions need all 5 of those phases. Most of the instructions, the R-type computational instructions, including a bunch of I-type instructions as well. Like, so you've got like add and add I, for instance. Like, so all the number crunching instructions, the arithmetic, logical, shift, and comparison instructions, they don't use the memory stage because they don't access the data memory because they're not loads and stores. So in that case, you only need to go fetch, decode, execute, write back. Branch instructions only need to do fetch, decode, and execute. They don't have to write back because they only have to update the program counter, not the register file. Loads actually are the only instructions that go through all 5 stages, and then stores just need fetch, decode, and memory. Oh, that's not true. Fetch, it should be execute in memory. How did I forget that? Yeah, fetch, yeah, you have to do execute for store because you have to calculate the effective address for the store. You guys remember that? if we were doing a single cycle CPU, so ARM Cortex-M processors and the Arduino processors, those are all single cycle instructions, single cycle CPUs. They execute one instruction at a time, and they do everything needed to execute the instruction in one cycle. One cycle, yeah. So anything it has to do, it's done at one time, and then you move on to the next instruction. The problem is that that's not always feasible. For one, single cycle limits your clock speed because you have to you have to assume the worst case. You have to this data path that has all of the stages hooked up in series sequentially for the load instruction, essentially, where you have to go through fetch, decode, execute, memory, and write back. But most instructions don't need that, but you still have to adjust your clock to allow for sort of the worst case in terms of workload for instruction. The other problem is that FPGAs in particular have their on-chip memory has a synchronous read, meaning that if you read an address from a RAM on the chip, on the FPGA, it has a one cycle latency. It takes a cycle. So if I try to read an address in cycle n, I won't get the result, I won't get the contents of that address until cycle n+1, which that alone prevents me from doing a single cycle CPU, because that means that in order for me to fetch an instruction, it takes at least two, I'll fetch it, but I won't have it until the next cycle. So if I only wanted to execute one instruction at a time, it would take at least 2 cycles, right? Because I'd have to fetch it in one cycle and do something with it in the next cycle. Then I have to fetch the next instruction in the third cycle and do something with that one in the fourth cycle, right? But likewise, the data memory has the same restriction. So if I had a load instruction, it would take 3 cycles, right? Because I'd have to fetch it, I'd have to access data memory, right? And then in the third cycle, I would have to write the results back, right? Because the load gets something from data memory and puts it in the register file, right? So at a minimum, I can't make a CPU on an FPGA in less than 3 cycles per instruction, right? So we will then just create a pipelined processor where you fetch in the first cycle, you do decode, execute, and memory in the second cycle, and then in the third cycle we'll write back, right? But then the pipelining will allow us to overlap instructions. So that way, while we're decoding, executing, and doing memory operations in the first instruction, we can then fetch the second instruction at the same time. And then by the next cycle, we can fetch the third instruction while we're decoding, executing, and memorying the second instruction while we're writing back the first instruction. Make sense? So that way, we can still achieve a throughput of 1 instruction per cycle, but we can still give each instruction 3 cycles to get done.
Right? The register file has both reads and write ports.
Right, and it's also why we did the bypass on the register file, because you can be writing register 2 in this instruction, this is n, right? But you can then be reading instruction 2 and instruction n+1, and because you're decoding that guy while you're writing back the other guy at the same time, you need that bypass, because this guy will be writing the new value of register 2, and it's going to pass it directly to this guy reading that value, right? Now, you guys might remember the 5-stage pipeline from 212. The 5-stage pipeline was a little bit more complicated because there was a difference of 3 cycles between when you write back and when you decode. So as a result, you had to have forwarding paths, right? You had to be able to forward data. Luckily, because we put decode, execute, memory all in one, we don't have to forward. The bypass is good enough for us, right, for data hazards. And that's why I did it this way, because I wanted to have one instruction per cycle, ideally. I wanted to have 3 cycles per instruction in terms of the latency of each instruction. But I didn't want to have to deal with all that forwarding stuff and load hazards and all the other consequences of the 5-stage pipeline. So we just do a 3-stage pipeline. Now, in the slides, we call the first stage of the pipeline fetch, and the last stage, the 3rd stage, write back. But what do we call the middle stage? Because it includes 3. What do we call it? Well, we call it execute, which is kind of confusing. So we have fetch, execute, and write back. But execute, in our terminology, means decode, execute, and memory, right? If you were to, using the terminology of the Hennessy and Patterson textbook from 212. You guys with me? Does that make sense? Okay. Okay, so how do these stages look? The fetch stage is really simple. It's really just the program counter connected to the instruction memory as well as an incrementer. So the program counter will increment every cycle, so it's just a counter, really. You guys have done counter. You did counter in your stack for the RPN calculator. So you just keep incrementing the program counter every cycle, and the program counter will be hardwired to the instruction memory, which will just be a RAM that's on chip. And the RAM, we set up the RAM in Verilog the same way we set up the register file, except we have to make the reads synchronous. And then the instruction just pops out, and it will be passed down to the subsequent stage, the next stage. You guys with me? So how do you do this? I'm showing you a schematic here, but how do you build this in Verilog? It's really simple. It's just a few lines of code, right? You just, this program counter is literally just, always underscore FF at pos edge clock, PC equals PC plus 1. All right, so that this is like one line just to do that. And then you use the PC to index the instruction memory, right? The part of this that confuses students in this class is, do we have to make a module for this? Like, how do we decompose this design into modules? Because Verilog has modules. You're supposed to use modules to create this design hierarchy. To be honest, I usually just put like everything in, like all the CPU stuff into one module, because there's not that many. I'm going to show you a lot of schematics, but when you implement it, it doesn't necessarily take that many lines of code to build this stuff in Verilog. Now, some of you would prefer to split up the design, to partition the design into modules for readability and modularity purposes, and it's better coding style, and that's up to you, right? I'm going to leave that part to you, right? The schematics are meant to convey the behavior, not the way that you decompose the system into modules. Okay, so how do we load a program then? How do we get a program into the CPU? It turns out, and this was just by luck, I was actually shocked when I found out how easy this is. If you go into Mars, you write a program, and you assemble it in Mars, which you've all done in 212, all you got to do is go to File, Dump Memory, and you can export your program as basically just a list of hex words corresponding to each machine instruction, and then you can use the readmem-h, which you guys have all done again in your test vectors for the ALU, to take whatever Mars gives you, and that can be read directly in to initialize the instruction memory. Yes?
That only worked in the simulator.
No, it doesn't. On an FPGA, you can use this to basically create a ROM, meaning that you have a RAM. You use the style of Verilog that creates a RAM, but you initialize
compile time, and that turns into read-only memory.
Right. Well, actually, I think it's actually not true. You could actually still add a write port. So it would initialize, like if you wanted to allow your CPU to have self-modifying code and risk, creating Skynet, then you could actually also put a write port on this instruction memory as well. But in this class, we usually just treat it as a ROM. So you create sort of the read port that you normally have on a RAM, and you initialize it with this, and then it becomes a ROM. And then in order to change your program, you have to reassemble it in Mars, re-export it, and then recompile on the FPGA. Or if you're simulating, you just recompile it in the simulator, and it will update your program automatically. So you can just point this to whatever, like you can dump directly to that file. So you go into Mars, you type in your code, you hit export, you recompile your design, and the program is updated. So it's pretty nice. Now, is Mars going to generate something our CPU doesn't understand? No, not necessarily. I mean, you just stick to the instruction set. That's what instruction sets are for. You follow the instruction set, and Mars follows the instruction set, and they talk to each other. They understand each other. They speak the same language. Yes?
So basically, like, we write a bunch of assembly programs using just the instructions that we know will work.
Yeah.
Feed it into Mars, dump it, and then we've got test benches.
Exactly. That way you don't have to write machine code, which is what I had to do when I was in undergrad school on the Intel 8085. Yeah, we had an Intel 8085. It had a hexadecimal keypad. It was like the damn Apollo guidance computer. You had to type in hex instructions one by one on a hex keypad. That sucked. Because we had to assemble them by hand. You still had to write them in assembly and then assemble them by hand on a piece of lab sheet and then key them in. Yeah, so at least this, what's that?
You didn't have assemblers?
No, we didn't. No, not that I knew of. For the Intel 80, no, not that I mean, they might have existed and we weren't aware of them, but back then we didn't even really have computers either. I mean, I wasn't that long ago, but some guys had a computer in their dorm room, but.
What happens if, like, a pseudo instruction generates an op that we haven't implemented yet? Or does
Well,
that not happen?
that'll happen. That could happen, sure.
So just gotta be careful with that.
Well, when you assemble in Mars, you can see there's a tab that shows you the machine code. So you just check the machine code tab. Make sure that it didn't do anything unexpected.
Yeah.
Okay. Okay. So that was the fetch. So that's all there is to it. You could build a very simple. Well, actually, it wouldn't do much. You could build this design. You initialize the the instruction memory with Mars, and you'll have an instruction stream. So that will generate an instruction stream. Then you have to have something to accept that stream and do something with it. So you have to start building these data paths. So you've got the fetch stage, which I showed you. And again, this cloud is not meant to represent a module. This is just represents the stuff I showed you in the previous slide. I'm trying to just kind of building this up incrementally. So you get the instruction stream coming out of the fetch stage, and you can take the fields 25 down to 21 and 20 down to 16. Those are your RS and RT registers. And you can connect those to the read address 1 and 2 on your reg file, right? Just hardwire them, directly connect them. So that way the register file will see the instructions coming out, and it will give you the contents of the registers that are at RS and RT for each instruction. Now you don't have to use them, but you'll have them available if you need them. You might say, why wouldn't we use them? Well, you might be doing a shift. I don't know, you might be doing a move from high or move from low instruction that doesn't need the registers, in which case you just ignore it or don't cares. Then you can take 10, okay, so which bits of the instruction needs to go into the control unit? What's the control unit do? It takes the instruction and decodes it into control signals. I haven't showed you any control signals yet. But what parts of the instruction determine what the instruction does in terms of the control? Well, obviously the op code, the function code, and there's also this bits 10 down to 6. What the heck is that? That's the shift amount. The shift amount we want to bring into the control unit. You might say, oh, wait a second, why don't you just take the shift amount and just connect it directly in the ALU's got a shift amount input, just connect it. Because sometimes we have to override that shift amount. Sometimes the control unit wants to force feed a shift amount into the ALU instead of just using whatever is in the instruction. And the particular case of that is load upper. There's an instruction called load upper immediate where we want to override the shift amount. But I'll get to that in a minute. So we'll take those. But you know what? You could just take the whole instruction and put it in there, right? You don't have to necessarily break out individual bits, because if you put bits into here that you don't use, then they get optimized out anyway. It's not like you're wasting any gates or anything there. Yes?
What happens to bits 11 through 15?
11 through 15, that is the RD field. And that will go into the write address on the register file. I just haven't showed it yet. And the reason for that is because the write back is in a different pipeline stage, so you don't want to connect it directly. You want to actually pass that through a register. You want to delay. So you're going to take those bits and shove them into the write address on here, but you want to delay it by one cycle, so you can push that into the next pipeline stage. Yeah. So in other words, you want the 11 up to 15 bits to represent the RD of not the current instruction, but the last instruction, right? That was fetched. Previous instruction that was fetched, which is what I show right there. Yeah, right there. Yeah. So that's exactly what that is. My diagrams are sometimes a little inconsistent. I try to make the registers this gray color. Sometimes I'm not consistent, and if I'm not, I'll point that out. And I'm going to try to fix that. But this is a register, a flip flop, a delay, puts a delay. Okay. We running out of time? Yes, we are. Okay. Okay, so let me speed up a bit here. Okay, so control unit, what's a control unit doing? Control unit has to tell the register file when it should write, because it doesn't always write. There's some instructions that don't write a register. Not many, but there's some, like the store instruction, the branch instructions, the jump instructions, the move from high, move from low. Or actually, sorry, move from high, move from low does actually write an instruction. Is that it? I guess that's it. Store, branch, jump. Multiply. That's what I was thinking of. Multiply writes to high and low register, does not write to a general purpose register. So there's a few instructions that don't write registers. Most of them do, but you have to be careful that you don't write a register. You don't write a register unless you need to. So that's why we have this reg write signal. You guys with me? The reg write connects to the write enable on your register file. But because it happens in the write back stage, we put a delay register there, right? Reg select determines what value we want to write back to the register file. And actually, let's see. Yeah, so there's, in this CPU design, we have 3 possibilities. What do you want to write to the register file? Normally, when you write to the register file, you write the output of the ALU, right? Like you do you do a number crunching instruction, and you need to update the destination register with the result. So for that, we're going to take this R register that comes out of the ALU. You guys with me? You guys say, why do you need a register? Because we want to take the output from the ALU from the previous cycle and write that into the register file. Make sense? Because it's because of the pipeline nature of the CPU. We want to, whatever we write in the register file will be the result of the previously executed instruction in the previous clock cycle. Right? So all you have to do to implement that is you delay whichever signals take effect in the write back cycle. Everyone with me? Okay. So when you guys did the RPN calculator, you did the same thing. Or you probably noticed that in the RPN calculator, you do an operation, you have to pop 2 values off the stack, and then you have to do something with them and push the result on the stack. The problem is that when you pop them off, they're gone. So you have to come up with a solution to that wherein you delay, whenever you do the operation, you push the result back on the RPN calculator, it has to be the values that were on the stack 2 cycles ago, right? And so that was the reason why one of the reasons we did that was because to get you comfortable with this idea of having to delay things. And that's what these things are doing. They're delaying signals for 1 cycle. So we can do something that are a result of the instruction that was being executed in the previous cycle. Now, the high and low registers are an exception to that, though. In that case, we want to potentially hold their value for multiple cycles. And the reason for that is because when you do a multiply, the high and low registers are updated and then they freeze, and they don't change until you do the next multiply. And that's an easy solution. You just have to have an enable, right? So all of these gray boxes are registers. Most of them don't have an enable because, and if I don't show an enable, that means they're always enabled, which means they change every cycle. But these 2 have an enable, meaning that if they're not enabled, they don't update their contents, which allows us to only enable them if you're doing a multiply, and then we can save the result of the multiply for as long as we need to, right? You guys with me? In Mars, by the way, they show high and low. They actually, when you debug your code in Mars, you can see high and low change when it executes a multiply instruction, and then those values are retained in high and low until the next multiply or divide.
So if you're holding the values for high and low in multiplication, those will be just held for however long.
Mm-hmm.
But in every cycle after that, you're still getting the write back from R, which would just
Right.
be low out.
Yeah, so R and low both take low from the ALU, but the difference is low only captures on a multiply, whereas R it's always sampling, or it's always updating.
Perhaps one way to think of it would be to imagine that the write enable on R is always high.
Yeah, and it is. I mean, that's how it's actually going to be synthesized onto the FPGA. It'll hardwire. You won't specify it in the Verilog, but in the hardware, it's going to hardwire the enable to high, because the hardware, the actual registers on the FPGA have an enable. They all have an enable, but the synthesizer will hardwire that high if you leave that ambiguous in the Verilog code, or I shouldn't say ambiguous, but if you don't explicitly have an enable that in the code. Okay. Okay, and then we've got the reg select, which allows us to select what we're writing back, R, high, or low. And so what this means is that this reg select almost always will be 0. We're almost always going to write R back. The only exception is when we have a move from high or a move from low instruction, in which case we want to select high or low here. But we have to be able to support that. So we have a MUX that will select those. Everyone with me? Okay. All right, so the one thing that's a bit confusing, or I think might be a bit confusing here, is we have these delays that are designed to separate the execute stage from the write back stage. The reg write is delayed, for pushing. So we have a reg write EX. Notice I added these suffixes here. So reg write EX is the reg write signal corresponding to whatever instruction is currently in the execute stage. And the reg write back is matching up to whatever instruction is in the write back stage, which is whatever was in the execute stage in the previous cycle, right? So that makes it a little easier to debug by having those suffixes there. Where was I going with this? Oh yeah. So actually, hold on. I'll revisit that in a minute. Let me go forward here a minute. Okay. So let's revisit the control unit now that we've got those diagrams. So what does this mean for the control unit? I mentioned the inputs are, we've got a shift amount and a function code. And the outputs are the ALU op. We have to tell the ALU what to do. And this is very similar to your RPN calculator that essentially did the same thing. You had a controller for the RPN calculator, had to tell the ALU what to do. The shamped, which is almost always just whatever's in the instruction 10 down to 6, but you can override it. Enable high-low is asserted only if you're executing a multiply instruction and not asserted otherwise. Reg select is usually 0, 0 if you're just writing back whatever's coming out of the ALU, but you're going to set it to 1 or 2 for a move from high, move from low instruction. And the reg write is going to be high or asserted whenever you're doing something that writes to a register, which is any of the arithmetic logical shift comparison instructions. You guys with me? Okay, so that's the inputs and outputs. So basically what this is just a lookup table, really. I mean, you can implement this as a I think the easiest way to do it is just big if then else. Just always com. It should be always com. Sorry, this is Verilog syntax. It should be always com here. This is just another way to write always com, always at star. Does it have to be in its own module called control unit? No, you could just put this always inside your top level CPU design. It's up to you. The way I'm showing it is I've got a separate module that does the control unit, but that's only because I've chosen to decompose the control unit stuff and put it in its own module. And I think that's actually a good idea, contrary to what I said earlier, because the control unit's can grow pretty big. It's probably a good idea to keep that in its own module. Yes?
If you're setting ALU shift amount to 5VX, does that mean you don't care?
You don't care, right? Just don't care.
Why wouldn't you just leave it like unset?
You can't leave it unset because then this will get converted to a latch. You have to set it on every control flow, on every, whatever the outcome of this always is, you have to set all your outputs or they'll be converted to latches.
Okay, and it's Verilog, so it's implicit.
Yeah.
So then why not just set the amount to 0 instead? Don't care.
You could, well, don't care just gives the synthesizer, presumably gives the synthesizer room to optimize your code more, to make the hardware more efficient by using the Karnaugh maps to reduce the number of gates. Does it actually do that? Probably not. I don't know. It's unclear how much logic optimization these tools do. But yeah, I just said it. It's nice though because in the simulator, if you set it to don't care, it'll come up as a blue line and it'll be really obvious that it's a don't care. So I think it's actually most helpful when you're simulating in a waveform for having that. Okay, so yeah, basically you're just looking at the function code. In this case, function code, if the function code is this or that, it's an add or an add u, respectively, in which case I tell the ALU to add, the shamped is a don't care, the enable high-low is a 0 because it's always a 0 unless I'm doing a multiply, right? The reg select is a 0 because otherwise the only time that's not 0 is a move from high, move from low. And the reg write is 1 because reg write is almost always 1 because I'm almost always going to write a register, right? There's a few instructions where I don't want to write a register, but yes.
Also, that should be an always com.
Yes, I mentioned that earlier. Yeah. This is the in case you're wondering, this is the Verilog way to do it. Now you might say, what's the advantage of always com versus always at star? It actually relates to Josh's question because Josh said, why not, or maybe it was, I don't know if it's Josh, why not just not specify the shamped? I said it would convert to a latch. And always underscore com will give you an error if you create a latch accidentally that way. Whereas this always at star will allow you to use a latch. It'll allow you to create a latch. And latches are almost always unintentional. And they do generate warnings when you synthesize your code, but you usually don't see them because it prints so much stuff out, yeah. So that's why you want to use always a com. It's an extra, it's kind of it protects you, right? Okay, so here's so what about testing? How do we test this thing? Write a program. this is my test program. I just put a one instance of all the instructions. And then I ran this through the simulator, and then I looked at the contents of the register file in the simulator to make sure that all the values were correct. So that's a test program you might want to use. Okay, so what I've shown you so far is just the R-type instructions. It gets a little bit more complicated, but not much more so to get the I instructions, the I-types in there. The I-types, what's the difference between R-type and I-type? Well, one, the destination register is RT instead of RD, right? So you have to add a mux for that, to select between RD and RT for your write address. Why in the world did they not just make the destination 20 down to 16 for all instructions, or for at least the R type and the I type, because then you wouldn't need that mux? Don't know, but I know they acknowledged that as a mistake, because if you look at RISC 5, they fixed it. And it was the same guys, by the way, that did MIPS. The guys that invented MIPS and RISC 5, same guy, David Patterson, in the team at Berkeley.
Instead of like updating MIPS to a new version or something.
Yeah, MIPS. So MIPS was the professors at Berkeley created MIPS, and then they created a company around it that licensed the instruction set. And then they sold that company, and they made millions of dollars. And then they spent the next 30 years complaining about how restrictive MIPS was legally. And then they said, oh, we're going to come out with RISC 5. It's going to be the world's first open source, non-licensed instruction set architecture, and we are the saviors that made this RISC 5. But what they forget to mention was that they're solving a problem that they created by creating MIPS. They created MIPS. It turned out to be a cash grab, and then they let everyone deal with that for 30 years. And now we have RISC 5 to solve that problem, but it's this
the best way to do it.
Yeah.
Solve your own problems.
Yep. Yeah. And that's exactly what they did, but it upsets me because now MIPS.
They created an answer to a problem that it doesn't necessarily need to be solved until they created it.
Right, exactly. No, but now MIPS, I hear, is now also open source because yeah, because MIPS. So Spark and MIPS, and there's this new trend in the industry where they're Power. Yeah, ARM will never do this because they make 100% of the revenue by licensing because they don't make chips. But yeah, ARM is, but yeah, so a lot of them are now going open source. But it's, we'll see what happens with that. But anyway, so we've got an extra mux here to select between those two guys, and we need to be able to add a mux here as well because R-type instructions do send two registers in the ALU, whereas an I-type sends a register plus the immediate. You guys with me? Okay. Now there's the sign and extend. I'm going to skip over that for now. I'll revisit that in the next lecture. I just want to get through enough of these slides so you guys get started. Yeah. So here's a test program that exercises the I-type instructions. There's not many. Okay, and then the last thing I want to mention is GPIO. We want to be able to run our processor on the FPGA and have it interact with the world, the outside world. We want it to be able to interact with, we want it to be able to do stuff. It needs to be able to take input in and write output out. It needs to have these peripherals, I/O devices. The problem is that we want to be able to do this before we implement load store instructions. Now normally computers talk to the outside world through load stores. That's how they communicate. They use what's programmed I/O, which is where you load and store to special addresses that create a communication channel. But we wanted to let that wait until the next lab to do that, so we came up with this solution. This is new this semester. We used to do this differently. But we came up with kind of a hack. But we thought, well, why don't we take advantage of some redundancy in the instruction set. If you do a shift right arithmetic and your shift amount is 0, we can treat that as a read GPIO in. In other words, we'll have a GPIO in signal coming in, and we'll put whatever that is into a register whenever we execute that instruction. Right? And likewise, if we want to send a signal out, we'll use a shift right logical with a shift amount of 0. Now you might say, why don't you use shift left logical? Well, because remember I mentioned that's actually a no-op. Right? That one's already used. Someone already claimed shift left logical as a special instruction, as a special case. Whereas these guys are unclaimed. So normally these instructions wouldn't have any effect on anything, right? Because if you shift by nothing, it doesn't change the state of the registers. But we can add some special stuff for this. So what do we need in the hardware to support that? Well, this is this is a little overwhelming, but this diagram is just everything I've showed you up to this point. I've put everything in. So I think this is a complete picture of the whole CPU. Everything you need. If you can just translate this to Verilog, you're done. Now, the color coding here is blue is modules. So obviously the reg file is a module we've got. The ALU is a module we've got. The control unit is a module that is basically just a big if then else. I showed you an example of that in a prior slide. The instruction memory doesn't have to be its own module. It just needs to be, you can inline that as a RAM, as just the initial block and basically just the and always that will generate an instruction from the address, right? So I show that as a blue, but it doesn't even have to be a module. It's just a little ROM, right? And then the dark gray are registers. Basically, always underscore FF at pos edge clock. So each one of these, and actually you could put all of these registers into one always block, right? If you wanted to, or you could have a separate always block for each register, or however you want to do that. And then the miscellaneous stuff is light gray, so muxes and this little sign extend logic. And I also gave you the code for the sign extend in lecture, I think it was lecture 2. I had it under the slide that talked about bit manipulations. It's just a sign extend, take the sign bit and copy it 16 times to convert the 16-bit immediate to a 32-bit value. Okay, so the GPIO, I added the GPIO stuff here. And the GPIO out is actually very simple. You just take whatever comes out of read data 1 and you just hook it into that. The only catch is that you want it to put in a register, and you will enable that register from the control unit. So when the control unit sees a shift, shift right arithmetic with a shift amount of 0, it'll enable that register. Done. That's all you got to do to make that happen. The other one, though, reading the GPIO in is a little bit more complicated because you have to incorporate that into this data path, this MUX, along with the high, low, and R registers here. Okay, so I'll leave that. I'm going to revisit this on next week, but I wanted to show you this so it's enough information for you to get started on the lab. Okay, the test program we want you to write is binary to decimal conversion. By the way, this is all explained in the lab sheet. Charles has a very thorough lab sheet that talks about all the requirements for the lab. We want you to write a binary to decimal conversion program that will read the switch values, convert it from binary to decimal, and then put it on the hex displays, right? So if you put 1111, that's 15. But you don't want to show F, you want to show 1.5, right? Because it converted to decimal, right? So we want to write a little program that does that in MIPS. Now you might say, well, how do you do that without divide? You have to divide to do binary to decimal conversion. You could do that, or there's actually a simpler way. And I'll talk about this more later, but you can also use fixed point. You can because anytime you divide by a constant, because in this case you have to divide by 10, and modulo by 10. Because that second operand is a constant, you don't actually need to divide. You just multiply by the reciprocal, right? So you just multiply by 1/10 instead of divide by 10. That's all you got to do. But how do you do 1/10 if you only have integers? Well, you have to use fixed point. Fixed point is you just assume you use integers, but you apply a scaling factor.
Oh, I've seen this done.
So-
actually. Like optimizing compilers will do this, so they can
Yeah.
multiply instead of.
So you don't have to use floating. You don't, because see, like in undergraduate curriculum, we often teach that anytime you need a fractional number, you should use floating point, but you don't. You can use fixed point to do fractional numbers and don't have to pay for the cost of floating point, which in our case, we don't have floating point hardware in here. But I'll go into more details in the next lecture, but I think you guys have enough to get started.